finishing chapter 2 today. There's a few more questions that I want to do on numerical summaries. I want to focus on quartiles and questions involving quartiles. And then I want, hopefully, in fact, we will move on to the last section in chapter 2, and that'll be chapter 2 over with. So here goes. And the first guy we're going to look at is question 12. So Mrs. Briggs needs to lose weight. Her doctor put her on a 1,500 calorie a day diet. And he tells her that she needs to stay below 1,500 calories at least 75% of the time. And that she also needs that her average, right, the mean, has to be less than 1,500 calories. And so over that 15-day dieting period, she recorded all the calories that she ate. And so we are now going to look at that data and find these numbers here. Okay. So I'm going to click use salt. And boom, here we go. Right, that's kind of nice, right? All the data. Which one of these guys along the top is going to get me Q1, the Q2, you know, the median, max, all that good stuff? Which of these will I be able to get all those summaries?
Descriptive statistics.
There we go. And there's a lot of numbers there, but the ones that we want are the lower quartile. So there's a new name. Which one of these guys here do you think should be the lower quartile?
Q1.
Yeah. And won't the upper quartile be Q3, right? So it's just another name for a guy you know. So I'll move this out the way so I can put them in. So, okay, what is the term? What is the term for the value that cuts off the lower 75% of the data? Right. So what do you think you call that guy?
Upper quartile.
Uh-huh. Oh, and I've put that in, but that was just pure accident. I didn't mean to put that in. And it says calculate the upper quartile, right? That's the guy that we had on the screen that you now cannot see, but I'll tell you what it was. The upper quartile is Q3, and that happens to be 1491. Now, according to her diet, shouldn't that be less than 1,500, right? That was one of the restrictions that the doctor gave her. So she's on Q for that one. Now, the next thing that we need to find is the mean number of calories. And the mean number of calories is, oh dear. $19.56. She didn't keep to her diet, did she? Wasn't the second restriction the average had to be less than 1,500 as well? I can tell you right now what I think happened to that poor woman, why she didn't quite make her diet. I'll try and make the numbers a little bit bigger because you may have a small screen. Okay, that wasn't something I meant to hit. I've lost this question number. What number was it? Oh, here we are. We found it. If you look at all the calories, can you see that there was a couple of days where she went off the wagon? I don't know if that's what you call it when you go off your diet. Didn't she eat 5,000 calories on that day? And then a few days later, she ate another 5,000 calories. So even although the median was correct, right? The median amount was that. weren't those two guys so big that they kind of broke our diet? So now I have to tell you a joke about diets because it just came into my head. This guy goes to a doctor and says, I need to lose weight. And he says, I've tried everything. I don't know. I just can't do the counting calorie. It doesn't work. You know, I keep breaking the rules. It's not working. Says, if you get anything for me. And the doctor says, I just read this article that says there's a new way to diet. The guy says, I'll try anything. What is it? He says, well, you can eat as much as you like for one day, but then you skip a day. And then the next day you can eat what you like, and then you skip a day. And that's how you do your diet. And the guy says, well, I think I might be able to do that, you know, as long as I can eat what I like, and then I can skip a day. And so he comes back a month later, and the guy has lost like half his weight. And the doctor is amazed, and he says, wow, that diet really works. And the guy says, it nearly worked. It nearly killed me. He says, what do you mean? He says, have you tried skipping for a day? Skipping? With a rope? Skipping? Oh, come on! Skipping? I give up. That's it. I'm not telling you jokes anymore.
No.
Okay, I'll tell you jokes because I like inflicting pain. So we're finished with that question, right? So that's just an example of, you know, some questions, they give you a term like the upper quartile, right? And you just have to know what that means. What's the next one? Okay, the next one is going to be question 13. Let's try that one.
Mr. Robinson, can you hear me?
I can hear you, yes.
Okay, I haven't been able to get my audio to work for the longest time. I just wanted to make sure. Thank you.
Oh, I just thought you were being quiet. So,
hand signals, they work great.
well, I'm glad that whatever you've got to do it, keep it. I had to, last night, my computer updated to Windows 11, and I was freaking out because, you know, when you do a major update, you lose your sound, your camera doesn't work, you can't log in, you know, the 101 thing. But so far, everything is going totally normal. So evidently, fingers crossed, things are good. So let's do this story. A small town in South Africa with a population of 850 has seen a large influx of patients with what's called the Zika virus. Evidently, this is a virus that causes birth defects. So you don't want to catch it, you know, when you're pregnant. There is a concern about the age of women in the town. So listed below are the ages of the latest female patients who come into the clinic who had the disease. So far, so good. Now I'm going to hit solve. And here we go. You can't see it yet, but I'll bring it on screen in a moment. Here is the data, right? And the first question is, what's the sample size? So I'm just going to say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. There should be, I believe, 20 people in that sample. Okay, now I'm going to bring over this guy. You see all the data, all the ages of the people. Was I right in my number? I was. There are 20 people. Do you see it in the bottom? And so I'm now going to go into descriptive statistics, which are all these numbers here. And 50% of the women in the study are at least what age? If you are using the 5-figure summary, if somebody says, what age is 50% of the people or less, isn't that the median? Right? At 40 years of age, aren't half the people older and half the people younger? Right? That's what the median tells me. If you go to Q1, right, the quartile one, At that age, isn't 25% of the people younger and the other 75% are older than 21? You see how the Q1s work, right? 25% are younger than 21, the other 75% are older. If you go to this fella, the 69 years old, right, the Q3, at that age, aren't 25% of the people who caught this 69 or older, and the other 75% are 69 and younger, right? So that's those numbers. Although they're going to disappear, try and pretend you remember them. So they talked about 50% of the women are at least this age, and so that ends up being the 40 that we talked about. 25% of the women in this study are under this age. Wasn't that the 21 that we talked about? And the 75% or over is 69. Are we all comfortable with those numbers and where we got them from, right? Isn't that basically Q2, Q1, and Q3, right? Now, if you look at the middle 50%, the middle 50% are 21 to 69, agreed? 21 to 69, which means then, the way I'm looking at that is, the other 50% are younger than 21 or older than 69. So can we throw those people out as not likely to be pregnant? Most of them, at least. Maybe you get an 18, 19, but most of them. So I think that is telling me that I shouldn't be overly worried, because aren't there a lot of people in the 40, 50s and age group that aren't going to be pregnant either? So there's a fair chance that less than half the people are at risk. Right. I'd be much more worried if 90% of the people were in an age range where you could get pregnant. That would be a bad thing, right? Useless piece of information, but it's analogous. Do you know that COVID, right, is not that dangerous unless you've got other medical issues if you're less than, I think it's 12, right? So if you're less than 12, the chances that you die if you catch COVID, if there was nothing else wrong with you, right? So if you had a heart defect or you were extremely ill, don't catch COVID no matter what age you are, right? Including being less than 12. But if you're less than 12, vast majority of them don't have a problem, right? In fact, the same number of kids who are under 12 die of the flu than died of COVID. COVID was not a young person's disease. A lot of diseases are, right? Do you know what COVID was a bad disease for? What age group?
Over 50s.
People with underlying health conditions?
Underlying health issues was true for everyone. You're right. Don't have a heart issue, don't have lung issues at any age and get COVID. Very dangerous. But apart from that, just normal people at a particular age, normal is a bad word, but people of that age who have no specific underlying conditions, 65 or over was the major death. That's what almost, not everybody, but a large proportion of those who died were in that age group. So if you were looking at COVID, wouldn't you be interested in what age the top 25% is? Because that would say to you, oh, okay, you know, how old is that? Because that could tell you whether the disease was going to be dangerous or not. And I think I'm finished with these questions because a lot of them are just finding and what we've done. No, I haven't done dot plot. I'm glad I remembered. Okay. Are you looking at question 18 here? No? Can you see question 18, students in a start class? That one?
Yes.
Okay, so I'm now going to show you how to create a dot plot along with a box plot. Right. So imagine that we had a set of data where, and this is the data I'm using here, where students in a statistics class were asked about how many minutes do you typically do exercise in a week. And the first group were self-identified women, right? and the second group were self-identified men. And although you can't see the numbers, and I'm not going to write them down because they take too long, we are going to compare these two groups using a dot plot. So you draw, just like you would do with a box plot, you draw a number line and you find the smallest number, which is 0. And you find the biggest number that you can find, and I'm scanning through them, and the biggest number I could find was 470. So I'm going to round it off to 500. And then you go 100, 200, 300, 400, 500. Now, what happens in a dot plot basically is that you put for each number, you put a dot where that would be. So for instance, the first woman did 70 minutes, and I would judge that 70 minutes is about there, right? And then the next person, the next woman did 230 minutes, and I would do a guesstimate of about there, right? And then the next one did 0, which means she was very honest, because I think a lot of them should have been 0, based on my knowledge of people at least. Right? And you do it. And when you're finished, I'm making this up. You know, you might get a guy that looks like that, right? And that's all a dot plot is, isn't it? You just take each number and make a dot where it is. Now, if you pretend that there's a line on it, can you get a kind of look that that's probably symmetric? You know, if you want to describe it. You then do the same with the males, and there are all sorts of combinations that could happen. I guess you'll find out what you get. Can you imagine a dot plot that looks like this? How would you describe the shape of that dot plot?
Right skewed?
That'll work for me. Skewed to the right, right skewed. Symmetric. Right. If there was going to be an outlier, in my picture here, wouldn't that be the outlier? If there was going to be one, right? You see the second last dot and the last one. Now you do a box plot. Well, you're not going to do a box plot by hand. So I'm going to now return to that set of data. And we're going to show you how you would get Salt to do it for us. Now, men, women, right? Men, women. Hit this guy. Here is the data loading up. I'm going to have to shrink the size a little bit so we can see it. Okay. I'm going to go to charts and graphs, and I'm going to do a box plot. And the first one can be women, and the second one can be men. What do you mean? Okay. I guess I'll have to do one at a time. Can you see the first one is the men? Is it the men? No, that's the women, right? You see that one? That's the women. Yeah, you have to do that left head thing, right? And then, can I do the men? I'll try and shrink this back. There. Now, watch that shape. Men, women. Men, women. Can you see that there's a little movement between the two? But they're pretty close to each other, aren't they? So I would say that there is little difference. Now I'm going to hit the dot plot. And okay, can you see? It's a pretty boring dot plot, isn't it? The real one. Right. I can't really tell if there's hills or anything or none. Or you agree? It's just kind of nondescript. If I did the main one, not much difference, right? Now, let's go to descriptive statistics, because I think the numbers help better than the pictures do. Let's do compare and contrast. The top row is women, and the bottom row is men. The average was about 3 hours for the women and a little bit more for the men. The median was 185 for the women and about 190 for the men. They're not perfectly the same, but would you agree that they're pretty close? Right, 185, 100. So they do ask you a question like, is there any differences? And I would say, no, they're pretty similar to each other. Right? So men and women exercise equally, and there's no discernible difference. And that's us finished that section. So we're now moving on to the last part of chapter 2. I'm going to do notes for most of today. And it's called bell-shaped data. This is not a joke, the thing I'm about to tell you, but it's an example of statistical information that sounds like it's telling you something important or useful and isn't. Do you know that half of all accidents on the road were caused by the other person? Isn't that true about everything? Aren't half of you got an IQ, have an above average IQ? Don't half of you have a below average IQ? Why? Because isn't the average in the middle? So don't you or at least if you use median, right? Isn't half them bigger than the median and half them are less than the median? Right? Don't half of you make more than the average? And don't half of you make less than the average? So you have lots of examples in data where people will tell you things, and if you just look at them superficially, you will think, oh, that's telling me something kind of interesting. No, it's not. Half of all accidents are caused by the other person, right? It's not telling me anything useful. So before we look at bell-shaped data, I want to take a side issue, and I want to show you some of the things you should be on the lookout, especially when politicians of either party try and bamboozle you with statistics, because two different politicians looking at the same information, right, the same data, can put quite wildly different interpretations on it, which I believe the jargon word now is spin. They can put their own spin on what that data is telling you. So I'm going to give you an example of totally made up data to show you how you can spin this in a way that isn't necessarily accurate. And what you need to ask yourself when you get data and they tell you this is what it means, is try and ask yourself, what other pieces of information would it be helpful for me to know to decide if what you're telling me makes sense or not? So here's my story. Did you know that Seattle police are racists? You didn't know that. They're racist against Scottish people. You might not think that Scottish people are a race, but I consider myself Celtic. I don't necessarily consider myself white. I'm not French. I'm not German. I'm not Italian. They're white. Well, actually, they're French, German, and Italian, but I don't consider myself that. I'm Scottish. I consider myself Celtic. I have a lot of affinity with the Irish. I have a lot of affinity with, obviously, Scottish people. I am definitely not English, right? So if you decide to pick people according to their race, and I consider myself to be part of the Celtic race, genetically you can prove that. You know, Celtic race is different genetically. There are markers that can tell the difference between me and a Frenchman. And they are racist. And how did I prove it? Only 2% of Seattle's police force is Scottish. See, they don't like Scottish people. They don't hire them. Only 2% of Scottish, right, in the police force in Seattle. That sounds like pretty good evidence, doesn't it? They're only 2%. They're racists. Yeah, I could believe that. What's missing?
The data
Well,
of applicants.
Right? Say again.
The data of applicants.
Right.
the
How
amount
many
of
people
Scottish
asked to join?
applicants.
Yeah.
Yeah.
That would
Also,
be important. Forrest?
also it could be if it might be you should look at the stuff like the age distribution, for instance, if say the Scottish community, it's mainly like retirees and stuff. So
Right. They're not going to join the police force. Yeah.
yeah, you're not.
Many
Or if,
applied.
yeah, or if it's mostly made up of like it's very young. So you'd want to look at, say, people range I don't know, 20 to 60. I'm not familiar with it, but yeah.
I gotcha. Well, I'm going to pick something very similar to that. I'm going to give you 3 scenarios for Seattle, right? So we'll assume that you're recruiting people from Seattle, right? So here's 3 scenarios, none of which are true, but for the context of this story, we'll pretend they are. The first scenario is that 40% of people in Seattle, right, are Scottish and are of the age that could join the police force. Now, if that was Seattle, yeah, I'm ready to start suing those guys. Would you agree if 40% of Seattle, right, is Scottish, how come only 2% of them get into the police force? I want to look at their hiring process, right? When they look at people as our applicants, if they see the word Mac or Mick on their last name, they don't even ask them to come in, because isn't that a good way of catching Scottish people, right? Does their name end in son, like mine's, right? You know, they just look through the names and say, oh, that's Scottish sounding, no, and they only pick ones that sound not Scottish, right? That would catch them. Would you agree that is definitely now enough evidence to be really worried about the hiring process in that one? Only 0.1% of people in Seattle are Scottish and could join the police force. Isn't that actually evidence the total opposite? Aren't there an awful lot more people in the police force compared to the percentage of Americans that live in, percentage of Scottish ancestry who live in Seattle? I mean, in fact, isn't that 20 times more? Isn't that 20 times less? Can you see that extra piece of information puts a whole new light on this piece of information? And the third one is, only 2% of Seattle is Scottish and could join the police force. Would you agree that's exactly what you would expect, you know, to see, right? So they're not racist at all. They actually have got some bias in favour of picking Scottish police, or they don't like Scottish people and they're not picking them at all. So when you are told a piece of information that seems very convincing, where you think to yourself, what other piece of information adds to the whole picture? Would you agree that once you know this and that, when you put them together, isn't that a much more realistic way of interpreting it? But you know what a politician's going to do? I tell you it right now, because I know they do it. It drives me crazy. Aren't they going to talk only about that piece of data? And that's what we have to be on the lookout for. So I know that was a side issue, but I think it's in my head, so I got it out. So here goes. Back to bell-shaped data. When we collect data, it's been noticed that a lot of the time, the data roughly looks like this. Right, there's a nice little histogram. And we have lots of names for these guys. I'll see if I can get all of them this time. Don't we call that symmetric, right? That's one of its names. Obviously bell-shaped. There is a third one that starts with the letter N. Can you remember what we call it when data looks like this?
Normal.
No skews.
It's called normal. Right? Totally interchangeable. I could use either of those words. I probably are going to, I don't know, I'm probably going to end up using normal a lot because that's what I'm most familiar with what's coming later. So far, so good. Now, we are going to look at what does the mean of a distribution like that look like? Where does it go? And we're going to look at another thing, SD for short, which is called the standard deviation. Now, the standard deviation does a similar job. To what the interquartile range does. It's a measure, it's a number, it's a measure of how spread out the data is. The interquartile range, we can do that by hand as long as the data is, 5, 10, 15 numbers. Right? I don't want to do it more than that, right? Because it's a lot of work. And you can certainly do it in your calculator, which is a little bit better. And you can do it with SALT, which is really nice, right? You hit the button and you just read the answer off, right? Q3, take away Q1. And this second fella called the standard deviation is horrendously ugly to do by hand. And if you look at one of my PDFs, I've done an example there and I've done it by hand, but nobody in their right mind would do it by hand, right? It's just a really messy calculation. So we will be doing the standard deviation by simply being told what it is in a lot of questions, or using the SALT button, or using the TI-84, right? So let me show you then on the calculator. I can find mine. Here we go. How to find this number called the standard deviation. So I'm going to pick, I don't know. Well, let's do the class data. Yeah, that's a good idea. Right. 2, 4, 5, 10, 15, right. So hopefully you're all going to answer, but if you don't, you're totally entitled not to. We are going to collect data on how many siblings you've got. So I want you to count you and your brother, so that would be 2. If you're an only child, it's 1, right? So count yourself. If there's 6 of you, including yourself, then the answer is going to be 6. And I'm going to use your data, and we're going to calculate the standard deviation of it, right? If you're willing to do so, right? And if you don't want to do so, that's totally fine. And Cheyenne's kind of got the idea of how we're going to do it, but I'm going to choose a little bit differently because it's hard for me to scan through numbers. So if you look at the bottom of the screen, there's a little icon. It's called reactions, and you can do a thumbs up. You see that thumbs up? So those people that I cannot see are going to have to vote by sticking that little icon. And for the rest of you, you're going to go, yeah, that's me, right? So we got the deal. So stick a thumbs up or show me your thumbs up if you are the only child in the family. I got 1. Oh, okay, 1. You and somebody else, 2 in the family. 1, 2, 3. 3 in the family. 1, 2, 3, 4, 5. I make that 5. 1, 2, 3, 4, 5. Anybody give it a chance for it to dissipate? Madison, yours should go away in a minute. Right, anybody got 4 in the family? 5? Cool. I like big families. 6? 7? 8? 9? Hey, I get to be last. 10. You do not know what you're missing, guys.
10.
So right, did anybody know that I missed them? They put their number up, but I didn't count it, and I'll add it right now. So I've got 4, 5, 6, 7, 8, 9, 10, 11. That's fine. So 11. So let's find the standard deviation. It's a number that basically tells you how spread out this is. And then I'm going to show you how to test for an outlier using standard deviation. Right? Remember we had the test when we used interquartile range for this is an outlier or that's not. There's a different test if you want to use the standard deviation. But first things first, you're going to hit the start button, which isn't a surprise. You're going to choose number 1, which is edit. And you're going to get rid of any old data that you might have. And you're going to go 1, 2, 2, 2, 3, 3, 3, 3, 3, 5, and 10. Just like you would do for interquartile range. You're then going to hit start. You're going to go over to calc, and you're going to, again, exactly the same. You're picking one variable stats. And I'm now going to tell it L1. Can anybody remember how you get L1 onto the calculator? How do I make L1 appear? What buttons do I press?
Isn't it second and then 1?
That's it. And then I hit enter. Now, if you look at this list of data here, right, all these numbers up here, there's quite a few things, but the only 2 that I'm typically going to be interested in these questions is the mean, which is about 3.4. And then we have the standard deviation. And that's a little bit tricky. So if you look really carefully, there's 2 numbers at the bottom. Both of these are standard deviations. The one that you're going to be picking is this one here called SX. And that is roughly 2.4. Now, the one underneath it is also standard deviation. That is a standard deviation of the entire population, right? I'm using you as a representation, right, a sample, right, of OC students, right? If I had actually got this data from every single student at OC, right, all of you, then it would have been a population standard deviation. You see there's a little difference, not a lot, but there is. So there is our guy. So I can tell you right now that the average number of siblings is about 3 and a bit, which seems reasonable. Would you agree? An awful lot of people pretty close to 3. And that the standard deviation is about 2.4. Now, if this entire list of numbers, is there anybody there that looks like it might be an outlier? Because I want to show you the outlier test. Agreed. 10 is. That's me. By the way, it's really good to have lots of kids. Well, in my opinion, it's a good idea to come from a family that's big, because it's just fun. My house, I was brought up in a house where it was never quiet. There was always something going on, right? So I liked it. It was fun. So here we go. How do you test for outliers? Using standard deviation, right? Using SX. Well, here it is. You find the mean and you add and subtract 3 standard deviations. Now the mean here is 3.4, and you add and subtract 3 lots of 2.4. So it's 3.4, add or subtract 7.2. And if you add these two together, you get 10.6. And if you take this away from the other, which I'm not going to risk doing in my head, if you do 3.4, take away 7.2, you get the answer negative 3.8. And this interval, right, any number between this number and that one is considered okay, right? You are not an outlier. If you're in that range.
Would
do you
you
notice
get the same exact answer if you used the other formula, the Q3 times or plus 1.5 times
IQR
Q1?
thing? Yeah. No, surprisingly not, you won't.
Or what does it mean?
No, the interquartile range one, right? Which is the one I think you're talking
Interquartile
about,
range.
right? Yeah. And that test doesn't give you the same numbers. That does mean that if you do a standard deviation test for an outlier, you might decide that something is an outlier, and then you do the interquartile range test and decide that it's not an outlier. You're just going to have to live with that contradiction. So make sure that you know which question you're in. So if you're in a question that's all about Q1s and interquartile ranges, doesn't that make sense that you're going to use that test, right? The Q3 add 1.5 IQRs. If you're in a question where it's all about means and medians, means and standard deviations, aren't you going to use this test if you've got it? Now you might say, and I can understand that, but come on, that's huge. And it is. But one of the things that standard deviation does, which kind of in a way makes it a better test, a more accurate test, is it uses all these numbers in its calculation. Even if I haven't shown you it, trust me, it uses all of them. And because it uses all of them, it's much more precise about what is an outlier. This data set is tiny. If you've only got a few numbers, isn't it dead easy to get one number that's quite different from the others? Only because you've only picked 8, 9, 10 people, right? If I randomly went out in the street and measured the height of 10 people, couldn't I get really unlucky and measure 9 kids and an adult?